So, welcome back student. As discussed in the last lecture, today we are going to talk about our guideline 4, which we have discussed in the very earlier lecture. We said our entire topic will be divided into 6 different guidelines: transformation, static material, functional group based strategies, which covers the 3 initial guidelines. The guideline 4 we will be talking about symmetry based strategies. Now, symmetry based strategies will trying to focus our discussion only for synthesis of symmetrical molecule, synthesis of symmetrical molecule. Now, actually in the nature there are many natural products which have been found perfectly symmetrical. Perfectly symmetrical in the sense that they have a nice sigma v plane of symmetry. So, in those cases what will be your guideline or what will be your strategy? The initial strategies, all these Fg, Tf and starting material will remain as it is. Only thing is you have to consider the symmetry element. Now, normally when we talk about the symmetry based strategies, one particular aspects we are basically not discussing here. We are not discussing the pericyclic reaction. So, pericyclic reactions are basically symmetry driven reactions or symmetry controlled reaction, but as we do not have that much time. So, probably pericyclic reaction is in true sense their symmetry controlled reaction, but these reactions we are not discussing at this moment. So, symmetry controlled reaction we will be trying to exclude this topic, we will not cover this topic at this moment or in this coursework. Now, for molecule which will trying to have a perfect sigma v, there might be a natural product as well as designed molecule. There exist many designed molecules which are perfectly symmetrical in nature. If I say now I drawing a molecule, now this molecule its name is cubane, this cubane molecule. This molecule is basically a hydrocarbon molecule, it is having only carbon and hydrogen. Now, this molecule as it looks like a cube, it is called cubane. Now, probably this is a design, this is basically a designed molecule, and this kind of molecule also can be synthesized with our standard knowledge of electrosynthetic disconnection. Now, if you see the cubane molecule does not have any active functional group, means is devoid of any functional group. So, in this case our guideline is you have to explore the redundant functionality. Now, normally this kind of designed molecule like cubane or other molecules are purely synthesized in terms of academic pursuit. They basically do not have any biological significance, as these molecules are devoid of any active functional group. There are molecules like cubane, prismane, garudane, housane. Probably we are not going to discuss all the structures. Now, for symmetry based molecule, you will often find that there are also certain guidelines or prerequisite which will be mainly following. Normally, we follow 4 different guidelines for symmetry based strategies, symmetry based strategy. And you say that the guideline basically focusing on 4 different points. Now, what are the 4 points? If you are trying to do a symmetry based strategies, you always maintenance of symmetry, or it is always advisable that if you start with a symmetrical intermediate, maintenance of symmetry is very important. You are going to make a symmetrical molecule, it is always advisable you start with a simple symmetrical starting material. And then we always will be talking about this particular terminology, local symmetry and pseudo symmetry. These two are very important terminologies, and sometimes you will find that the entire molecule is not symmetrical, but part of the molecule is symmetrical. So, there is a local element of symmetry in the structure, and due to this presence of some different functional group, the entire molecule now becomes pseudo symmetrical, means it looks like symmetrical because one part is having local symmetry, but the entire molecule is pseudo, means this from the very beginning or just by looking it looks like symmetrical, but due to presence of that functional group content it is pseudo symmetrical. We will talking about some molecules where the local symmetry and pseudo symmetry is included and what are the strategies. Then we will find that particular desymmetrization is also very important strategical guideline which falls under symmetrical based strategies. What are desymmetrization? We will be trying to having a very brief idea of desymmetrization based strategies. And then point D we will try to explore the whole this three different guideline and we will try to synthesize some of the symmetrical molecule. So, this will be our main point of discussion, synthesize some of the symmetrical molecule. Now, as I said, the symmetry is basically we are talking about only sigma v, mainly sigma v, and for your information, this particular two symmetry element mainly sigma v and C2 and sigma v plays a very important role in synthetic planning. And this particular two symmetry element, how it plays a very important pathway in the synthetic planning, we will talk about in stereochemical strategies. In addition also this two symmetry element is very important in symmetric control pericyclic reaction. As we are not discussing it, but for your information you will come to know that the sigma v and C2 plays a very important role for predicting the selection rule in pericyclic reaction, which is purely symmetric controlled. So, now we will try to explore the things. We said that it is always advisable to start with a symmetrical intermediate. Now, we will talk about some case studies. We will first try to do a retro for a symmetrical molecule. This molecule we have discussed in the introductory video lecture. This molecule is named as adamantane, is basically a hydrocarbon. It is a hydrocarbon. Now, adamantane, if you see its structural features, is the purely hydrocarbon. It does have a 3 cyclohexane ring in a condensed fashion, and all the 3 cyclohexane rings are basically chair. Cyclohexane ring are in chair form. So, that gives a very nice structural network. Now, if you see the adamantane has a nice plane of symmetry, if you try to draw the plane which basically goes through this, and then you can basically have a nice bisecting into 2 equal halves of this molecule. Now, you can basically visualize the molecule if you have a nice 3-dimensional model. So, this molecule having a nice sigma v. Now, I say we will try to maintain the guideline 1, that throughout the pathway, if it is possible, we try to disconnect that the symmetry maintenance was done. The initial guideline or initial I will try to give you a hint that the starting material was something like this, starting material was giving to you. Now, actually our strategy will be similar based on the exploration of redundant functionality. We will be using key transformation. Now, let us do the initial retro. The initial retro which was proposed by keeping the core structure similar, okay, it is a little bit wrong structure. So, as I said that drawing needs to be perfect. We will try to put a carbonyl group here and as well as we will put a this carbonyl group here. We say that if you can deoxygenate both the carbonyl groups, you can get the adamantane. Now, this is nothing, this is basically a beta keto ester which you can easily hydrolyze to get the beta keto acid, which you can heat, which will decarboxylate to give this compound. So, initially this is now again a sigma V, because the plane goes with this. So, this sigma B visualization is very important. So, sigma B the intermediate. So, next what I am saying? I am saying that we will try to have a Dickman kind of transformation, which will basically give you this intermediate whose structure is now like this. We will put a CO2 Me here and we will put a CO2 Me here. We are saying that this CO2 Me having a hydrogen here, which will basically forms this carbon ion and then it will undergo Dickman reaction with one of the CO2 Me group to give this thing. So, this transformation is your Dickman reaction, which is very obvious. Fine. Now, this molecule does have a sigma V. Fine. So, now if you find that it is a cyclohexanon based compound, 4 position is having CO2 Me, CO2 Me, CO2 Me, CO2 Me. The starting material is basically now we are trying to visualize. The starting material is also symmetrical starting material. The only thing is what you need to do, you basically need to do one carbon carbon bond formation here, one carbon carbon bond formation here to close the cyclohexane ring. Now, the way it has been done, you take the starting material CO2 Me, CO2 Me and take this compound, this compound. Now, this compound is very unique. The starting material of this compound basically having a Michael acceptor at one end. In addition, it is having a electrophilic allyl bromide at one end. Now, this initial cyclohexanon based compound, what it can be done? It can be first generate a carbon ion and then it can basically undergoing a Michael addition here. Okay. And then in addition, this compound also can be generated a carbon ion here to trap with this electrophile. So, this compound serves as a double electrophile and then this compound serves as a double anion, doubly charged anion. Then basically you get this particular compound. So, now let us do the synthesis which was proposed as the forward pathway. So, initial starting material CO2 Me, CO2 Me, you react with double bond CH2 Br CO2 Me. Now, I am saying basically a Michael and a alkylation. So, it is a Michael as well as enolate alkylation. Now, pathways operate and then we now try to write the core structure in the chair form. This part will remain similar CO2 Me, CO2 Me. Here one of the CH2 group is now coming here and this CH2 is basically giving you this another CO2 Me. So, see it is basically now absolutely done. So, if this minus attacks here. So, this minus attack this CH2 okay, and you get this CO2 Me. This CH2 here attacks here. So, basically what are the bonds you made? You made this bond, you made this bonds. So, now next you treat with sodium ethoxide for the Dickman reaction. This anion is generated, it reacts here and then it basically gives you the another 6 member chair form and so it is basically minus, it will be having double bond O, it will be having another CO2 Me also here. So, now you just basic hydrolysis and heat. So, decarboxylation from here, decarboxylation from here. Then after this decarboxylation basically you will get the ketone here, you get the ketone here. Now, all the intermediates are essentially symmetrical, it is sigma V and then you do a Wolff-Kishner reduction by exploration of redundant functionality, you get the target molecule. So, if you now see the entire pathway we strictly followed the symmetry maintenance. So, you said the symmetry was maintained very perfect way. Try to analyze a similar kind of molecule. This molecule is bit unique structure. It is a 2 5-member ring fused in linear fashion and the another 5-member ring was basically fused in this way. The structure was basically drawn in this way because in a 2-dimensional form. So, this is a ring A, this black is ring B and this red is ring C, all are 5-member rings. Now, this kind of compounds which basically possess a common carbon-carbon bond through a particular vortex, these compounds are basically falls in class of propellane. You probably have seen the propeller which have a common axis, then you have the cycle. So, basically you have this cyclic structure through a common bond and this particular 5-5-5 framework is normally named as modifane. Now, normally modifane kind of compounds it is also named as 3-3-3 propellane because 1-2-3, 1-2-3, 1-2-3, 3-3 propellane. Now, this modifane class of compounds or this kind of compounds are available in the nature. There are basically naturally occurring compound this core framework, but the compound which I am now given or drawn here it is sigma V containing compound, it is perfectly symmetrical. Now, the retro we will be trying to analyze it and we will say that this retro is purely based on maintenance of symmetry element and exploration of redundant functionality was the main key transformation for accessing this molecule. So, this thing was and you are having this CO. So, 3 symmetrical carbonyl has to be reduced by Wolff-Kishner reduction to give you this molecule. This molecule is having sigma V. Now, your disconnection was bit interesting because now what we now do it, we will put a linear or acyclic structure and we propose that 3 round of Dickman cyclization takes place with the help of this gives 1 round of Dickman means this minus with this. So, this is 1 round of Dickman, this is 1 round of Dickman. So, give this 5-member ring and this is another round of Dickman with this 2 CH2 CO2 Me. Basically, this alpha carbanion reacts with this another carbonyl. So, it is basically Dickman. Now, this one is also can be called as a sigma V, fine. So, now try to again simplify how these compounds can be made. This compound we propose that can be made starting from this compound by simple ozonolysis. Okay. Now, this we said okay, you can is this is also sigma V. So, symmetry was basically maintained, symmetry was maintained. This we say if you have this diol, you can simply do the FGI, normal FGI, and then this retro we are now closing here. We said if you having a diene and if you having a dienophile like a triple bond mediated dienophile and another round of diene. So, now we will do the forward synthesis to see how this pathway looks like. So, you have a diene plus acetylene dicarboxylate. So, first round of 4 plus 2, you basically come here. Okay. Another round of cycloaddition with this diene, and then basically you will get this compound. Okay. So, next you reduce the compound with lithium aluminum hydride excess to get the corresponding diol, which is one of the intermediate for this. This alcohol you need to now convert to corresponding ester by simple FGI. You do a tosylation followed by sodium cyanide, do the cyanide hydrolysis and then put the diazomethane. So, basically you do the diazomethane, that basically gives you the compound CH2CO2Me, CH2CO2Me. Now, here what you do? You now next do the ozonolysis, that will give you the aldehyde here. So, ozonolysis aldehyde, then you can oxidize the aldehyde to corresponding acid followed by another round of diazomethane. So, ozonolysis oxidation of this aldehyde to corresponding acid followed by another round of diazomethane, you basically get the symmetrical acyclic compound, which was proposed as one of this intermediate. Now, this intermediate will now undergo Dickman reaction as discussed earlier. So, basically how this reaction will takes place, this minus will react with this carbonyl, this minus will react with this carbonyl, this minus will react with this carbonyl. Now, actually there is a different complex situation may arise if there are cross reaction might takes place. That is why probably the yield of this reaction will be not very good, and probably you have a difficult scenario if the cross Dickman takes place. So, probably we assume that the Dickman reaction is done in very perfect way, and you can close the ring as mentioned in the target molecule. So, after this Dickman and decarboxylation, you basically will end up with this linear thing, and then here we will write these things as this ring. So, now is Dickman followed by decarboxylation is obvious, and then you complete the target. So, eventually this kind of aspects of a given symmetrical molecule is very important, and you need to consider it when you talk about, and you would remember that symmetry maintenance was the main criteria, we always keep it in our mind. So, we will continue our discussion for this perfectly symmetrical molecule in the next week also. We will see you in the next week. Till then, goodbye, have a good time.